technology for the training and also inference, especially in the cloud. And also FPGA has become popular, especially for the inference at the edge. And also companies are developing the basic solutions. For example, Google's TPU to do the inference and training both at the cloud and edge to further specialize the hardware for their workloads. And in the past lectures, we have talked about the computing memory, which is a new paradigm to do the machine learning MAC operation. And in many cases, we can use a mixed signal and compute mode to further boost the energy efficiency. But of course, we must consider the degradation of the accuracy when we do the mixed signal and compute. This is because we will suffer from the variations, and also in many cases, we have to deal with a low precision computation. So a big question mark is the accuracy if we do the computing memory. So this needs to be benchmarked before we do the actual implementation. So here we still believe that the computing memory is a good candidate, but mostly for the edge inference, where the model is pre-trained. Of course, we can do some training on the computing memory platform as well, but I don't think the training should start from the scratch because it's very expensive to update the weights locally on those non-volatile memory. So it's better that we do the mostly inference. Maybe in some cases, occasionally, we can do some weight updates. So it's like an incremental or lifelong learning. So here, then we develop this NeuroSim platform. We want to use it for early stage design exploration. And we can evaluate different device technologies for computing memory. And recently, we have extended the platform to support the general AI hardware beyond the computing memory. Okay, again, this is like a recap of what we discussed before. So most of the computing memory uses mixed signal and compute mode. And the neural network is mapped to the memory array, and the input is mapped as the voltages that could turn on multiple rows. And then the weights of the neural network is mapped as conductance of the memory cell. So the voltage multiplied by the conductance gives the current. And then we sum up the current along the column. So end of the column is that partial sum current. This is the dot product between the input vector and weight matrix. And somehow we need to digitize this partial sum current to the digital domain. And then later we can do the digital post-processing like shift and add to reconstruct the significance of the precision. So we have talked about the device technologies in the previous lectures. So SRAM could be a standard CMOS implementation, but we also have more compact 1T1R and FE-FET implementations, as we discussed in the previous lectures, where the conductance of this variable resistor or the conductance of the channel due to the shift of the threshold voltage could be used as the weights. And they could be programmed into multi-level, so we can have multi-bit weights in one cell in principle. So this is still like a review. And then let's look at a benchmark at the device level. So here, if you look at this table, it shows the key metrics for emerging memories compared to the mainstream charge-based memories. So we have the mainstream technologies like SRAM, DRAM, Flash, NOR Flash, NAND Flash, and the emerging non-volatile memories. We talked about the RRAM in the previous lecture, but we also have other candidates like distributed memory, MRAM, either STT or SOT MRAM, and also the FERAM, FE-FET, as we discussed last time. So here, if you look at the metrics at the single cell level, so this is how it looks like. So we compare the cell area in terms of F square. F is a feature size, like the technology load. Then, of course, the non-volatile memory in general will be smaller than SRAM at the same technology load. But it's very hard to compete other high-density memory like DRAM or Flash especially Flash, because today we have the 3D NAND Flash, where we can have like 300 layers. Then this could make the cell area equivalently to be 4F squared divided by 300, and then divided by the multi-bit cell, for example, 3-bit per cell. So then the effective area per bit is very, very small. So that's why the NAND-based SSD becomes so cheap these days. So it's impossible to compete with the NAND in terms of the density from any technology. But here, if we care about the performance, like the read time, write time, then those non-volatile memories would generally be better than the flash and could be comparable to the DRAM, but it's very hard to beat SRAM in terms of the performance. So SRAM is very fast, sub-nanosecond. But here for most of those emerging non-volatile memories, it's very hard to operate below 1 nanosecond. So SRAM still needs to be used for the low-level caches on chip. And then in terms of the endurance, then there's a wide range for the emerging non-volatile memory. Generally, it's better than the NAND flash or no flash, but not as good as SRAM or DRAM, which you can operate almost all the time. So here, the non-volatile memory is somewhere in the middle. And in terms of the write energy, then it's more expensive to write than the SRAM. And because SRAM removes the charges, here, the emerging non-volatile memory, you have to change the atomic configuration. So it's more expensive. And so the only competing technology would be the FEFET, as we discussed last time, because it's field-driven. We do not pass the DC current. So the write energy could be small for the FEFET. So those are the metrics at the device level, but we want to understand how we translate those device level metrics into the system level. We have to evaluate not only the device technology, but also the peripheral circuits and the overall chip architecture. So the question we want to address, which emerging non-volatile memory is good for computing memory application? To answer this question, then we developed this NeuroSim platform. So it's an open source simulator for AI hardware. And we started from the computing memory accelerator benchmark. So this is a web page from GitHub for our simulator. And this is the link, and you can take a look, github.com/NeuroSim. And I would say this is like a pre-RTL simulator for early stage research. So this is not running RTL, this is not running SPICE. So this is running our custom codes to evaluate the PPA, the performance power area for those chips if we implement the emerging non-volatile memories for the computing memory. And we have multiple versions. And the latest version is this NeuroSim 1.4, which was updated a few months ago. So overall, the NeuroSim has attracted wide attention from the community. And we have over 500 citations from other papers using our tool. And we have hundreds of users from the academic groups and also the industry researchers. For example, we have active collaboration with SK Hynix, Samsung, TSMC, and Intel, and we support their researchers to use our tool to evaluate their own technologies as well. So here, the NeuroSim has won many awards. For example, we have won this IEEE transaction on computer-aided design TCAD and Best Paper Award this year. And the student who contributed to this NeuroSim development won the European Design Automation Association Outstanding Dissertation Award this year as well. So the tool is becoming very popular in the research community. So here the latest version, as I mentioned, is this 1.4. So here a brief history for the NeuroSim. So we started the efforts long time back, around 2015. And this is the first appearance. So my first PhD student, Payu, who actually graduated from National Taiwan University, joined my lab and started this work. So we presented in a workshop called Hello, co-located with ICCAD. So at that time, we supported only the multi-layer perceptron, very simple, fully connected two-layer neural network model for the MNIST dataset. So it's only for this small 100-digit recognition. And we published the paper in the IEDM 17 and the follow-up journal at TCAD 18. And then we realized that we have to generalize the support beyond this simple MLP. So later, my other student, Xiaoshan, who just won the award, as I mentioned in the previous slide, and now she joined TSMC as a hardware engineer. So she started this effort to integrate the NeuroSim with the popular machine learning package, for example, PyTorch. So we can then run the generalized neural network model using a custom interface between the PyTorch and our NeuroSim code. So we can support arbitrary neural network as long as you define the network model in the PyTorch, and then you can run the training and inference in the PyTorch before you export the traces from the PyTorch to the NeuroSim for the hardware estimation. So the inference version was published in the IEDM 19, and then the follow-up training version was published in the TCAD, which won the best paper award. So I would acknowledge the contributions from my former and current students listed in here who have greatly improved the platform over the years. So here is some statistics for the impact of the NeuroSim. We have hundreds of publications cited NeuroSim or used the NeuroSim for their research. And we have supported a major industry for their internal research as well. And there are many users around the world using our tool. Okay, so then let's talk about the methodologies in the NeuroSim, especially the DNN plus NeuroSim platform. So here is Python plus C++ code. So Python is used for the interface with the PyTorch because PyTorch is in the Python. And then the NeuroSim internal code is written in C++. So here we have different versions. But in general, we take the input parameters, including the device level, circuit level, and architecture level, and data flow. So those will be our input parameters, and then coupled with the algorithm, which is defined as a neural network model in the PyTorch. So here, if you look at the input parameters to the tool, we could have the experimental device data from different emerging number-time memories. And also we can choose the technology node for the preferred circuits. And then we define the neural network structure in the PyTorch in terms of the data set, model, and weight precision, and so on. So then we could translate those into the input parameters to the NeuroSim on the device level, circuit level, and algorithm level. And then we run the NeuroSim, and then we will get the entire chip level simulation through the equation-based models. And we'll discuss that in a minute. And so it's not SPICE simulation, because if you run the entire chip in SPICE, it will take forever, maybe a few weeks to finish the SPICE simulation. So it's impossible to quickly get the results if we are at the early design stage. So we want to get the results quickly. So here we simplify those circuit modules into the equation-based model. So then the output from the simulator, on the algorithm level, we report the accuracy. So this accuracy is the accuracy under the hardware constraints. It's not the same as your software baseline, because here in the hardware, we have so many non-ideal effects. For example, the precision is limited, and also we have the device variations, noise, and so on. So the accuracy may be lower than the software baseline. So we report this accuracy. And then we have other metrics, mostly the TOPS, tera operations per second per watt, throughput divided by the power. This is energy efficiency. And then throughput area and the breakdown of those metrics. And so breakdown means we can decompose those area and power consumption into modules. So we can look at which module of the circuit consume the most area or the power. Okay, so here are some high-level features. So here for the neural network training and inference, we support the quantized training and inference, because in the hardware implementation, we have to mostly deal with the fixed point computation, generally used in the ASIC design, because it's very difficult to support the floating point computation in the ASIC design. This is unlike GPU. And so then we have optimized the data flow, and also we support different network models. For example, for a moderate model like CIFAR10, CIFAR100, and we also support the large data set like ImageNet. So we have the default models like VGG or ResNet for those data sets. And then we have the PPA, performance power area estimation, for the circuit component at the module level. So we have the models for this key component, like ADC, level shifter, deep flip-flop, adder tree, and so on. So here, those modules are calibrated with SPICE at module level, not the entire chip, because entire chip, as I said, if you validate that, it will take like a few weeks. So, but each individual module has been validated. And then we have a variety of the options. So we can support the technology node from 130 nanometer down to today's, not today, I mean futures 1 nanometer. And then we can choose different memory technologies and choose different device parameters. And then we have different ADC options as well. So for the interconnect, we have mostly the H-tree routing from the subarray to the higher hierarchy. And so here we have estimated the RC delay due to the prosthetics. And then we also consider off-chip DRAM access. So this is needed if the data model could not be stored entirely on chip, then you have to frequently access the data from the off-chip. And also, as I said, there are many non-ideal device or circuit level effects which will hurt the accuracy. For example, the device vibrations, noises, ADC will introduce quantization loss, and also ADC offset will shift the partial sum from the ideal value. So we have to take care of those non-ideal effects when we evaluate the accuracy. So this is the key features from the tool. So let me go through some methodologies for the area estimation. So it's very straightforward. So depending on the memory technology, then we choose the memory array and configuration, and get the array area. Depending on the memory cell area, then multiply by the array size. So then we get the array area, and then we have to consider the peripheral circuits. For example, then the decoder. So we have to consider the decoder specs, and also we have to size the decoder to maintain the speed when you activate the VRLAN. So you have to size up the decoder's driver accordingly due to the loading of the cap. So then this will define the size of those transmission gate or the inverters. And then we also need to support the ADC area. So ADC actually is typically large compared to the column pitch of the memory. So let's say, ideally we want one column to have one ADC, but in practice, if the ADC area is large compared to the column size, so multiple columns have to share the ADC. So we have this ADC max sharing. So typically we do 8 share 1 or 16 share 1 to accommodate the layout constraints. So we can get those area estimation through this flow for the subarray, and then we could get the follow-up like either tree, shift register, and other area components. And then the latency, so it's also through the equation. So if it's read latency, then we mostly need to consider the RC delay in the digital block, and then the equivalent R based on the transistor's performance. So especially the on-state current, and this could be temperature dependent, and also the C mostly is the load to the wire, and then we have the RC delay from the wire resistance or wire cap, and also the transistor string cap, which is attached to the bitline wire. And then for the peripheral circuits delay, because it's ADC, so it's very difficult to simply use equation to model that. So we have to run some space simulation in Cadence, and then build a lookup table or equation and to fit the ADC delay as a function of the input equivalent column resistance. And then we have to consider the operation scheme, because sometimes the latency during the critical path, and so some of the latency could be hidden. And for example, when you enable the decoder, at the same time you can enable the mux, so you can somehow hide those latency if you run those in parallel. But of course, we have to consider the critical path, which you have to run sequentially. And then, for example, in general, if you think about the one subarray, then you activate the VLAN, and then the input voltage come in, and then you have to consider propagation delay for the input voltage to the memory cell, and then activate the cell, and then get the column current, and then you have a column delay, and then through the mux, and then the ADC. So there's a critical path for you to get the results. And then dynamic energy estimation. So then again, for the energy, mostly we consider two kinds of energy. One is the dynamic energy, mostly the CV square for the wire charging. And then for the digital block, it's also CV square for the digital gates. And then for the memory, beyond the CV square, we need to consider the static energy, because you pass the current, then there's a static energy component depending on the rate voltage and then the rate current. And then for the ADC, again, we have to use a fitting function to get the ADC power as a function of the equivalent input column resistance. So this is how we get the total energy for the one read operation. So here, as you say, it's mostly the equation based, and we have to consider all the critical paths and then the major components for the area energy contributions. So next, let's look at the V1. So V1 is for the inference engine and benchmark. So here, this is an overview. We have this Python wrapper to interface between the PyTorch and our own NeuroSim C++ code. So basically, in this wrapper, we define the neural network model. You can define the network structure, how many layers, each layer, how many kernels, and what is the size for each kernel. So then we can evaluate the algorithm level accuracy using the PyTorch, but considering the device level and circuit level non-ideal effects, as we mentioned earlier. For example, at the device level here, if the device retention has a problem, for example, if the conductance of the cell will drift over time, then the weight will drift over time. So that will impact the accuracy. So as the time goes by, then the inference accuracy may go down. And also for the ADC, because it has limited precision, so then we have to truncate the ADC and using some reference for this partial sum distribution. Then depending on the ADC quantization and precision, then the accuracy may change. So here just to show two examples in the device or the circuit, non-ideal effects may affect the accuracy. So we can support other non-ideal effects as well in the simulator. And then this is for the circuit, for the algorithm level. And then here, when we do the hardware estimation, so we have to export the traces from here. Traces means the overall chip floor plan, and depending on the how many tiles, how many layers of the neural network, then we have to map those layers into a tiled chip architecture. So here within tile, we have the here if you look at here the hierarchical design. So the entire chip will consist of multiple tile. Multiple tile will consist multiple processing elements, PE, and one PE may consist of many synaptic subarray. So we have this hierarchy of the chip floor plan, which could support with many layers of the computation. Of course, some layers may occupy more tiles, some layers may occupy less tiles, depending on the network structure. But here we try to optimize the data flow to maximize the memory utilization. And also the traces include the actual synaptic weights and then the neural input activations. So we need to save those weights and the activations to the hardware, because for the weights, we have to unroll that and then map that to the kernel and eventually to the memory array. And then the activations is input. So we need to load in the activation and map and multiply by the weight in the memory. So here, then depending on the actual activation and actual weight, then we'll get different, the partial sum on current. So we need to calculate the current, because different current will give you different power consumption. So here, then we have this mapping and partition and strategy. So then we can evaluate the entire chip architecture. So for example, layer 1 only occupy one tile and layer N occupy 4 tiles. So in the actual operation, so there are two modes to run the inference engine. One is layer by layer, which is a natural mapping to the neural network. The neural network is also layer by layer propagation. You finish the first layer computation, then you move to the second layer. So that means you activate this tile, and then after the computation is done, then the intermediate data is transferred through the H3 routing to the next layer and start the computation. So you can do this layer by layer computation, which is a natural mapping. However, when you are doing this computation in one layer, the other tiles will be in idle. So those tiles will consume the leakage power. And also the throughput is limited. So what you can do is to do the pipeline. And then that means you can partition the entire neural network into multiple stages, and then you can do the staged pipelining. And then that means you can do the partial processing of the one image and using certain layers. And then you are, for example, you are using here this part of the chip to process the image one. Then you can use this part of the chip to process the image two, at least the first few layers. So we can do this pipeline fashion, as long as you can balance the latency between the stages. So here this is the hierarchy, as we mentioned earlier, from the chip breakdown to the tile, breakdown to the PE, and then breakdown to the subarray. So from the chip down to the PE, the overall architecture is similar. So we have many of those tiles, PEs, or arrays. And at each level, we have the input and output buffer. And then we also have the adder-tree accumulation circuit to do the partial sum accumulation. And then at the chip level, we have some other modules to do the special functions like the activation and the pooling. So this will be mostly digital circuit. And the activation mostly could be done using the lookup table. So here, if you look at the subarray, we call synaptic array. So we have different design options. So we can support the S1 based subarray. So if you look at the one subarray, you break down that, you have the S1, and then you have the decoder and driver, precharger, ADC, adder, shift register. So this is mostly the S1 based one subarray. And then you can have options like two-terminal or number tile memory. So 1T1R, basically, this R could be RAM phase change memory and other memory, two-terminal resistive memory. So you have 1T1R, and then you have the input switch matrix, and then you have the MUX, ADC, and the post-digital processing. And similarly, we can have the FE effects based design. So we have different design options to choose from. And then here shows some examples how we evaluate the early design space exploration. So basically, we have many options in the design. So we want to look at the trade-offs. For example, this is for simple BGG8 C pattern data set. And then here we can vary the subarray, the synaptic array size from 64 by 64 to 128 by 128, 256 by 256. Then we can vary the ADC precision 3-bit, 4-bit, 5 bits for the same technology. I believe this is RM. So here you can look at the trade-off between the efficiency and then the area and accuracy. So here, of course, with higher precision of ADC, you see that accuracy is much improved. And then the array size, if you have large arrays, the 1 over area, this is large, but that means the memory utilization would be lower because large array. So here, let's look at this memory utilization metric. So if the array is large, but in some cases the kernels are small, like 3 by 3, and then you have 128. So if you unroll everything, it will not be able to occupy the entire array. So the memory utilization is low. That means many of those cells are useless. So this is when the area, the array size is too large. But if the array size is too small, then and the area is not very efficient. So due to the peripheral circuits, you have too many peripheral circuits if the array size is too small. So that's a trade-off in terms of the design and optimization. And also here for the accuracy, this is specific pattern data set. You see that generally we need a 5-bit ADC to maintain the accuracy. And especially for large array, then 5-bit is a must. But if the array size is smaller, then depending on the cell level precision, if it's 1 bit per cell, then 4-bit ADC may be okay, but still there's some degradation. So the recommendation is 5-bit ADC. And in terms of the ADC, there are different types of ADC. So there are 2 popular choices. One is a flash ADC. Basically, you have multiple comparators in parallel. So then the bit time voltage will be compared at one time, and then through the comparators, then you can have the thermometer to binary encoder afterwards to encode the digital bits. So here, as you can imagine, then when the ADC precision increases, the number of the comparators will exponentially increase. So 3 bits, you need 8, let's say 7 comparator. 4 bits, you need 15 comparator. So this is very expensive in terms of the area and the power. So alternatively, for high precision computation, then we generally recommend the SAR-ADC. So you have one comparator, and then due to the SAR logic, you can compare the voltage by changing the references through the capacitive deck array, and then you can compare the beacon voltage in multiple cycles. Of course, this is slower, but it is more scalable in terms of the area and power when the precision goes up. So we have done some space level simulation for simple voltage mode SAR ADC and flash ADC, and also here the trend shows that above 4 bits due to the area and then the power consumption. So we would recommend the SAR ADC above 4 bits. But below 4 bits, the flash ADC is good. And so here we also have supported the current mode comparator. So here for the SenSam, this is typical voltage mode SenSam, and then this is typical current mode SenSam. So we have supported both types of the SenSam. So generally, current mode, if the current is small, then current mode SenSam is faster than the voltage mode. So here then the weight mapping and duplication strategy for pipelining. So here we consider how to map the convolutional neural network into the memory array. Because convolutional kernel is a 3-dimensional kernel, and you have multiple kernels, then essentially it's a 4-dimensional tensor. But then the memory array is a 2-dimensional array. So we have to map this 4-dimensional tensor into 2-dimensional memory array. So that means we have to somehow unroll this high-dimensional tensor into the low-dimensional matrix. So the different mapping strategy for this unrolling. So here, for example, a conventional mapping is going to map, okay, let's say one kernel, let's say 3 by 3 by 128. Then you map the 3 by 3 by 128, roughly it's like 1,000 elements into a long column. And then for the input picture map, you also unroll this to the same dimension. So you can do the you can scan over the input picture map. So let's say from this first cycle, you're loading the first one, 3 by 3 by 128. Then you can do the computation, and then you shift the window. Then you get the second one, and then you do the computation. So you can get the output vector also in this cycled fashion. And then you can map those output vector into this output feature map. So this is conventional mapping, but then it's not very friendly to the memory array, because this could be very large, like 1,000 by 1,000, but then the memory array could be smaller in due to the limitation in the RC delay. So if the memory array is smaller, then this conventional mapping is not very friendly, because you have to cut this into multiple smaller arrays, and then you cannot run this in parallel. So here we have a novel mapping strategy. In here, for example, we are going to map the same location of different kernels into the same subarray. For example, here, let's say 3 by 3 by 128. But we look at the first element in this 9 by 3 by 3. So the first element, 128. So here we map this 128 to here, and then the second 128 to second corner. So then for different subarray, we're going to map different locations. For example, the last one will be the length element. So we put it into the length array. So here we have NAND arrays to map this 3 by 3 K by K a matrix. And then when we do the input loading, then we can also only look at the first element, and then we can load this partially to this first array. And meanwhile, we can load the other input feature map to the other arrays. So we can run those in parallel. And then through the accumulation, we have to sum up this partial sum and then reconstruct to save it back to this output feature map. So basically, we can still preserve the parallelism in the computation by using smaller but more efficient, more utilized subarray sizes. So this is a better mapping strategy for the data flow, which is friendly to the computing memory. So through this mapping, we can also do the localized, it's like a systolic array, because in the different time cycle, then we're going to shift the input feature map from the neighboring, and because here we have neighboring subarrays, and then the input feature map will be first used by this one, and then after we this array used the feature map, then this feature map could be moved to the next array for the scanning of the window. So here we show this kind of a shift in the cycle 2. Then you see the input feature map of this one will shift to the input feature map of this one, and we have this kind of systolic array operation. So this could save the data movement of the input feature map as well, because the input feature map will be just locally sent to the next array without traveling a long distance over the chip. So this is useful to minimize the data flow. And then we can also consider the duplication, especially if you think about the general convolutional neural network. So the shallow layers, which means the first few layers, then the input feature map volume is high, but the kernel is small. So the kernel size, 3 by 3 by 128, even you unroll it, it's like 1,000 elements. But the input, if you look at the images, like imaging at hundreds by hundreds, a few hundreds by a few hundreds, you get like tens of thousands. So then the shallow layers are typically slow because you have to scan over the entire images through this kernel. Kernel is small. So the strategy here is to duplicate the kernels for the shallow layers to speed up. Because we have to do the pipeline, then the shallow stages and the deeper stages is to have the similar latency, but shallow layers are slow if you do not do anything. So here then the strategy is to duplicate the weight of the kernel into multiple memory array, and then you can run this convolution in parallel. So then you can speed up. So this basically is to use the space to trade off the time, because you have the space in the memory, then you can duplicate that, and then you can do those convolution computation in parallel. So this could speed up and then make the total pipeline smooth. So then, of course, depending on how you do the partition and then how you do the pipeline, then you can choose the so-called the degree of the weight duplication by a factor of 2, factor of 4, by factor of 16. So this is a design parameter we can choose from the simulator. So here we also did some validation of the component level of the chip of the simulator's prediction versus the real chip, because we have designed the R1 chip as we presented before. We have done the tape out with TSMC and 40 nanometer R1. So we have the full control of this chip. So we know the the block level latency area and the power. So here we can do the validation of the NeuroSim. So for example, the deep flip-flop NeuroSim estimated using the 40 nanometer design rule is like this area, but the real chip is this area. So then we have to adjust this by some factor. And then also for the latency and energy, you can do similar thing. So I would say for the area estimation, we are pretty close without doing anything. So you look at the shift add components, we have deep flip-flop, adder, inverter, and then accumulation, and also we have this component. So here, the area prediction is pretty close to the layout. And then for the energy, we are off by certain factor. So here, if we multiply by this factor, then we can get close to the real chip. Those factors are introduced because in our NeuroSim, we couldn't consider the transistor sizing. And we can size the transistor a little bit. For example, the inverter that drives the VLAN, depending on the VLAN's RC. But then, for the digital logic that control here, in the synthesis flow, then the EDA tool will automatically adjust the transistor sizing to meet the timing requirements. But we cannot do that in our estimation. So we will have to use some fixed transistor sizing for the deep flip-flop, for the adder, and so on. So then we have to consider some adjustments to consider the sizing effect. And also we couldn't consider too much on the routing due to the wiring. So sometimes in the layout, the area is consumed by the wires. But we couldn't consider the wire area in our estimation. And also for the energy. So one thing is in the real chip, if you run the RTO, then run the test vector, then you will have the actual gate switching activity depending on the workload. So the gate is not switching 100%. So here in NeuroSim, we couldn't consider the actual workloads of each individual gates. So we have to consider multiply by the gate activity factor. And then post layout, there will be performance drop due to the prosthetics. So we have to consider that as well. But if we add this kind of factor in those non-ideal effects, then we could get close to the real chip estimation. So that means in the NeuroSim, so after the equation-based prediction, we can introduce some factors to consider some of those effects. But of course, those factors will depend on the technology node, and we couldn't do that for all the technology nodes. But at least for 40 nanometer, we have validated by those by adding those factors, we can get closer to the real chip. But even without adding those factors, we are pretty good, at least on the same order of those energy and area estimation. So here then we show the benchmark results using the simulator for this, for example, CIFAR data set on this VGG8 network, which runs 8-bit activation and 8-bit wait. So here then we can choose different technology node and different memory devices, and then we get the device data from those published paper from the major foundries, and then we choose different precision, and then the key parameters from the device technology will be on-state resistance, and then the cell area, on-off ratio of the device, and then here we can get the chip level performance PPA. Area-wise, you see that those areas. And so generally, then here we can boost the energy efficiency. So even though R-run, M-run, those could be smaller than S-run at the cell level, but due to the expensive ADC and also the peripheral circuits dominate the chip area, as we discussed before. If you look at the layout of our previous chip. So then at the chip level, the area does not really show too much benefits than the SRAM. implementation. So the key improvement would be the energy efficiency. If, only if, okay, the on-state resistance of the device is high. So here, for example, the MRAM is actually worse than the SRAM in terms of the energy efficiency. Why is that? Because MRAM, the cell current is too large compared to the SRAM. So the energy efficiency is not good. But if we can increase the on-state resistance from this 1 kilo ohm to 200 kilo ohm due to the ferroelectric field effect transistor we discussed before, the channel conductance or resistance could be tuned by the gate bias. So it's a 3-terminal device. So you have much wider dynamic range to tune the on-state resistance. So if you can get this on-state resistance, then you can boost the energy efficiency. So this is the key learning from this exercise. So here, for any non-volatile memory to be competitive, this is the target range for the on-state resistance. If you cannot do this, then there's no competition with SRAM. So here for the SRAM is still good, especially for more advanced node. So this exercise was done like a few years ago. So at that time, 7 nanometer is the best technology available. But today you could have 3 nanometer, and in the future you could have 1 nanometer. So SRAM is a scalable approach. So it's still good. So that's why I said before many times, for high performance computing, SRAM is still the best choice for the data center. But still here we do the computing in memory in SRAM. So this is still limited by the process variation and noise and so on. But in terms of the performance, the leading edge node SRAM will be the best. But here, this is analog computing with SRAM. So still this suffers from the noise and variations. So the accuracy is still a question mark. So then the non-volatile memory is good for the edge edge inference at this no-cost platforms. Especially we can increase the on-state resistance like in the FEFET. So here is a visualized benchmark from the data from the previous table. So I showed that 7 nanometer SRAM is still good in terms of the energy efficiency, and 22 nanometer FEFET is also good in terms of the energy efficiency. And then in terms of the compute efficiency, that means the density, TOPS per millimeter square. So here, then 7 nanometer design, of course, due to the technology advantage, it has high TOPS per millimeter square. And FEFET, at least in the 22 nanometer platform, is good. So to improve the density, we have to scale the technology node. There's no doubt about that. Then what is good for the non-volatile memory? For example, the FEFET. We have to consider is the standby scenario. So here in this initial benchmark, the system is always 100% in use. But in the edge, because if there's standby idle period, then here we have this ratio, computation versus standby ratio. Let's say 1 is 100%. That means you are doing the computation all the time. Then the 22 nanometer FEFET and 7 nanometer SRAM, as we show here, they are comparable. But if we lower the computation ratio, so that means more idle time, you see that the energy efficiency of the FEFET will be better than any other technology, better than this 7 nanometer SRAM, because SRAM is leaking during the standby. So we have the leakage power penalty for the SRAM. So that's why the FEFET non-volatile memory, you do not have the leakage, then it shows better energy efficiency if the standby is frequent. So here we show that FEFET is good in terms of the TOPS per watt, especially at the low computation ratio. But here still the TOPS per millimeter square here, this one is lower than the 7 nanometer SRAM because the technology node difference, because here is 22 nanometer design rule, and this is 7 nanometer. So of course, this is at disadvantage. But my question is, how can we improve this one? Even we do not further scale the FE-FET, because scale FE-FET to 7 nanometer node will have faced a lot of challenges for the device itself. But if the technology does not really scale, then what would be the option? So here we show the roadmap for improving the FE-FET-based computing memory. The goal is to beat the 7 nanometer SRAM equivalent design by 10 times in terms of the TOPS per watt and the TOPS per millimeter square. So here, this is starting point. Energy efficiency wise, TOPS per watt, they are similar, as we discussed, 22 FE-FET and 7 SRAM. But then the TOPS per millimeter square is much lower. So we have to improve the density of the FE-FET. First, the step one is to reduce the FE-FET rate voltage if possible, because the area of the FE-FET chip has a large component of the level shifter to change the voltage domain from 1 volt to 3 volts for the programming. So if we can reduce the voltage, rate voltage, then we can get rid of the level shifter. Then we improve the area efficiency here to here without level shifter. And if we can do the multi-bit per cell, so in the initial benchmarking, we assume only 2 levels in the FE-FET, the 2 threshold voltage IV. But if we can do 2 bit per cell, 4 levels, then we can improve the density, and meanwhile improve the energy efficiency as well. And if we can do 4 bit per cell, that means 16 levels. Of course, this is challenging, considering 2 bit may be okay, but 4 bit per cell is quite tough for today's device. But let's assume if we can do that in the future, then you can boost to here. So then you barely beat the density as the SRAM. But how do you get the last point here? 10 times better in terms of the energy efficiency and the computing efficiency. So the only way is to do the 3D bit cell. So this is the only way. So the idea is that for the FE-FET, we have to move it from the front end to the back end of the line. So here, my collaborator, Professor Sumandata, has demonstrated the back end of the line 3D FE-FET, at least a single device demonstration. So the FE-FET is folded on top. So you can have the pure memory array on top of the interconnect. So you don't consume the area of the ferro memory array at all, because here this is on top of the interconnect, and here the channel is not silicon. The channel is the indium oxide, constant doped indium oxide, IWO channel. So you can have the memory entirely on top of the peripheral circuits. So you save the memory arrays area, and also here the peripheral circuits. Since you decouple the memory design and then the peripheral circuits design, so the peripheral circuit design could use more advanced design rule. For example, the front end of the line transistor could be designed using 7 nanometer load, even though the back end of the line, here's FE-FET, would stay at 22 nanometer design rule. So then you decouple the design rule from the front end to the back end, and then you save the entire array, memory array area, and using advanced design rule for the front end peripheral circuits. In this way, you can get the highest density and the best performance. So this is the future. If we want to, develop the FE-FET based computing memory and to really beat the SRAM version. So there's a long way to go, but this is a pathway for the future. So we just showcase how we use the simulator to help with this kind of roadmap definition. Next, I will talk about the training version. So for the training, it's more difficult than inference because you have to support many of those back propagation operations here. So this is similar framework as before, but the difference is highlighted in this part. So you have to consider the back propagation for the training, which means we have to update the conductance of the device. So there's pulsing scheme to do that. Given the programming pulses, then you can change the conductance, but then it may not follow the ideal trajectory. So when you give the pulses, then the conductance may increase or may decrease non-linearly, and also asymmetrically. So here there's a symmetry and a non-linearity. And on top of that, we have device vibrations, cycle-to-cycle vibrations. So this weight update curve is not ideal. So that means from the back propagation, you have the ideal delta W. But when you write the delta W to your weight, then the new weight may not be what you want. So then this will introduce the training accuracy convergence issue. And also to support this back propagation, we have to add the hardware components to do this backward calculation, especially the gradient computation. So here, let me just quickly go over the flow for the training. So there are 4 stages in the training of the neural network, if it's back propagation based. Then here we have multiple layers, and then the first stage is same as inference. So you have the input data, and then you do the convolution with weight, and then you get the partial sum, and then you do this layer by layer propagation. And then for the training, then you will have the supervised label with your prediction, and then you compare the prediction with the true label, and then you get the error. Then you have to back propagate the error. So error will be the input and multiplied by the transpose of the weights. Then you get the delta error, and then you do the back propagation this way. So this is the second step. Once you get the error or the stages, then you have to do the gradient calculation. So the gradient calculation is at each layer, the error from here multiplied by the intermediate activation from here, from the first step. You do this matrix multiplication. Then you get the delta W. This is the gradient of the weight. And then on the last step is the W plus delta W. You update the weight with this gradient. So this is the entire loop for one epoch. So here then the intermediate data, like this Y, needs to be stored for some time, because here you first get the Y1, and then you have to finish the entire propagation, feed forward, and then you have to wait for the backward propagation all the way back to here. And then you get the arrow delta 1. And this delta 1 needs to be multiplied by the here the Y1. So Y1 is to be stored for quite some time after you finish the entire feed forward and backward propagation. So that means for the training, we have to generate and store a lot of intermediate data. Because in the inference, this Y1 could be discarded, throw away right away after you finish the first layer, and then you use this for the second layer, and after that you can throw it away. You don't need it anymore. But for the training, you have to store it, this one. So you need to generate and store this intermediate data. This is a huge challenge in the on-chip design if you do not have the DRAM off-chip. So that's why still we need the DRAM in the training. That's why GPU equipped with high bandwidth memory. This is because this intermediate data. For example, even for this small network, VGG8 Pacific button, for batch size 200, we need like 2.6 gigabytes volume to store those intermediate data. And if you have other network, it will be like tens of gigabytes for the intermediate data. So this means the fragment data reload from DRAM because on chip buffer, SRAM cache, no way to store gigabyte level data. So then the off-chip DRAM access will dominate the entire energy consumption for the training, even we do the on-chip training. So this is a big challenge for the training accelerator design. Unless we can, innovate the training strategy for the neural network, but for now, this is a standard way. So we discussed if we want to write the weight directly into the emerging number type memory devices, we suffer from this normalized conductance versus the number of rate pulses problem. So ideally, it should be this dashed line. So you give a one pulse, and then the conductance weight increase or decrease linearly. But in many actual devices, the conductance will increase, follow this blue trajectory, and decrease, follow the red trajectory. So this is asymmetry in terms of the conductance increase and decrease, and also this is nonlinear. So if we have this behavior, then the write is not ideal. So then the weight update will have some problem. So here we analyze this problem. For example, here, if we follow this trajectory to do the weight update, then what's the problem? For example, in the few batches, few cycles, then this weight needs to increase the conductance. So we follow, this is an example, okay? So we follow this. But then now the next step, if the gradient calculation give you a negative span of the weight of the update, you have to decrease the weight. Then in the actual device, you have to follow this red trajectory. So that means the conductance goes from here, and now the negative one pulse will decrease the conductance a lot to here. But this is not ideal because the elective sign just want to change this a little bit, but due to this asymmetry, you change a lot. So statistically speaking, it's easier for this network to converge with this kind of distribution because most of the conductance will concentrate in the middle because a sign change will change a lot. So here the idea is to introduce the momentum and for this weight updates. This is to mitigate this problem. So here we design a new weight update rule. So the weight update not only depend on the current gradient, but also depend on the previous few steps. So we have to accumulate the momentum of the weight update and then decide the next one. So this is what we introduced to overcome the challenge of this non-ideal weight update behavior. So here, this is the equation. So basically, we have to accumulate the delta W from the previous step and plus the current step. So we want to prevent this sudden change due to the sign of the change. So here are the training traces, training accuracy versus number of epoch, and for different nonlinearity ratio. So here, let me go back. So here we label this. Let's say from 0 means it's a perfect linear, and then none means very nonlinear. So we have this degree of the nonlinearity, and positive means blue trajectory, negative means red trajectory. So we have this varied in the weight update. So the baseline training, you see that for button you get like over 90% accuracy, but as you have a large nonlinearity, then you cannot converge and get the good accuracy. So, but with the momentum, then we can recover some of those loss. So here, this is the results. So here you see that without momentum in this technique, then with a little bit nonlinearity, you drop a notch. But with this momentum, at least for the a slight nonlinearity, we can still maintain a better accuracy than without momentum. But still, this is a problem in general for the training if your device is not behaving ideally. So that's why the training is so difficult with this memory devices. On top of this nonlinearity and asymmetry, we have the device-to-device variation. That means different memory cells may follow different trajectory. There's a sigma variation across this median value. And also from cycle to cycle, it may not be this smooth curve. You may have the fluctuation along this weight update curve. So we can also evaluate those effects into the training. So here we introduce for example, the device-to-device variation for different nonlinearity. Then we can look at how they behave. But here, to our surprise, so with the device-to-device variation, even to like a few percent, then here the accuracy could still be good. This is because the training, is an iterative process. So the system may, may be annealed to different local minima. So if you have device-to-device variation, then you will have different solutions to the final problem. So it would be okay if the device-to-device variation is within certain range. But if the device if you have the cycle-to-cycle variation, then could be more harmful to the accuracy. This is because the cycle-to-cycle variation will quickly degrade the accuracy, because if you have the cycle-to-cycle variation, then it's more like a random updates to the deterministic updates based on your gradient calculation. So if the cycle-to-cycle variation is too large, then it will overshadow your gradient calculation. Then the system will not converge. But a little bit cycle-to-cycle variation actually is okay. It's okay. But then this really depends on the degree of the variation. But generally, if the variation is too large, then the network will not be able to converge. Okay, then for the system level performance, so here we show some results for the F effect based training on chip training. So here, I will skip the breakdown of the components. So here is a breakdown for different components. For area, latency, energy, we decompose that into the ADC, the memory array, buffer, interconnect, the DRAM, and so on. So then for the different stages, we also break down that into the those 4 stages: feed forward, backward propagation, and the gradient calculation weight updates. So here I just want to highlight a few conclusions because it's difficult to read all the details in the table. I just want to highlight the conclusion here. The conclusion is that the buffer latency and DRAM energy is a bottleneck of the performance. You see here this one, this dark green is all DRAM energy, then over 94% in terms of the energy consumption. So this is as what we discussed. You have to frequently store the intermediate data back to DRAM and then load it back when you do the calculation. So DRAM will become the dominant component in this case. And then in terms of the overall entire learning, again, if you look at those 4 stages, weight gradient calculation stage will take most of the energy and latency because you have to reload from the DRAM to do the calculation. So this is not very friendly to the training if you do not have a good DRAM. So here I believe the DRAM we used for the estimation, this was done a few years ago, is LPDDR4. Yeah, nowadays you have a LPDDR5, maybe will improve a little bit on the overall performance, but it will not change the conclusion. Still, DRAM is a bottleneck. So that's why we believe that training is not very feasible. Even we have done this exercise, we don't believe that training users those emergent number memory will be a good practical design. First, it suffers from the accuracy loss due to the non-ideal device effects. Second, then the DRAM will dominate the overall performance. So its meaning is to optimize on-chip component if the DRAM is a bottleneck. So we believe still the inference would be the best target for this computing memory, especially for the edge applications. Now let's look at the extensions of the NeuroSim platform. First, we want to talk about the technology support down to 1 nanometer node, and then talk about the DSIM support. So this is a potential candidate to support the high performance computing application, because as I said, so computing memory with the emergent number memory, even with SRAM, then suffer from the accuracy, and also the technology platform may be 22 nanometer for this number memory, so it's not good for high performance cloud servers. So here to support the cloud server needs, we have to use most advanced technology node. That's why we predict the technology node to futures 1 nanometer node. And also, we have to support the digital domain computation. There's a proposal from TSMC 2 or 3 years ago to do this DSIM with SRAM. So we believe this is the way to go for high performance computing. So let's take a look at this extension. So here we actually have many extensions of the NeuroSim platform, but I will talk about that DSIM support in 1 minute. But here let me go through all the support extensions we have done. So the first extension is to support the reconfigurable design, because the initial NeuroSim will just map a neural network to a specific chip architecture. So it's one network, one chip architecture. And you cannot use one chip to support different network model. So if you want to do that, you have to add some routing and configuration to the chip to have the reconfigurability. So I have supported that. So one chip would support different network model, of course, with some overhead in the routing configuration. And then monolithic 3D. So we already show some examples. For example, what we discussed earlier, the FEFET at the back end of the LAN would be one example. So to do this 3D partition monolithically with backend of LAN technology. So here we show RM, but we believe the FEFET backend of non-FEFET would be more promising. So you can have the 22 nanometer FEFET here and the 7 nanometer front end design. And also beyond the monolithic 3D, we could also support the heterogeneous 3D. That means we have multiple chips, and we do the die stacking by the advanced packaging, for example, with the TSV and hybrid bonding, micro bumps. So then we supported those designs as well. And we will talk about the 3D support in the future, next lecture. And also we have the cryogenic NeuroSim. That means if you want to use those chips in lower temperature for data center environment or for the quantum peripheral circuits, then you have to update the technology library at 4K and 77K, because the transistor performance will be very different. So we have the calibrated device model for the low temperature 4K and 77K transistor characteristics, and then we updated the technology file for the cryogenic operation. And also 3D NAND, we have supported 3D NAND, which is very different from the embedded memory. So we have different architecture to support the 3D NAND. And I believe I will also talk about that in the next lecture when we talk about the 3D IC design. So here, quickly go through the reconfigurable design. So basic idea is to have different data flow when we reconfigure the network, because we have the fixed hardware, and then we have to support, for example, different feature set, a number of elements in let's say 4x4 PE, and when we have 3x, the predefined number of PEs is 3x3 within one tile. Then what do we do here? So here, this is an ideal partial sum data flow. So you can have those 16 together, and then 16 together, and then you accumulate or sum up those. But since we only have 3x3 PE, then we have to do this in different cycles, and then do the sum accumulation vertically along this with more like 3x3. Of course, then we have some unused PE due to the reformatting. But here, again, with the 3x3 PE, we can do this 4x4 PE accumulation using this kind of data flow. So then this is, to sum up, this is partial sum will be vertically accumulated and horizontally concatenated. So this is the way to do the output accumulation due to the limitation of the hardware, because your predefined hardware is 3x3, but now you change the network to be 4x4. And then this is one example we have to deal with. Monolithic 3D we discussed a little bit before. So besides FEFET, then at the backend we have to use a backend NAND transistor, and we have modeled the backend NAND transistor, for example, the indium oxide-based transistor, and then updated the technology support for that. And then here, this is an exercise. If we do the 3D partition, for example, 45 nanometer design rule for the oxide transistor as a backend, and 7 nanometer front-end transistor, then we can get the very competitive energy efficiency and throughput and so on. This is using the RRAM as example. Let's say 45 nanometer backend RRAM plus 7 nanometer front-end silicon. This is also gives the best performance, outperform the 7 nanometer pure front-end silicon with SRAM. So this is similar as what we showed earlier with FEFET, 22 nanometer FEFET compared with 7 nanometer SRAM, but that FEFET is backend FEFET. So this is the only way to go, I think, if we want to make the non-volatile memory competitive. So we have to do it backend. And heterogeneous 3D, if you want to map a larger system, so then we have to stack multiple chips. So here, for example, we have 5 dice. If we can bond those 5 dice vertically using the TSV and the hybrid bonding, then we can do the data flow vertically. So we can have a logic die and the multiple memory die all have the sandwiched and logic memory. So we can do the entire neural network like this propagation like vertically. So then, and this is a design exercise, of course, and we have to take care of the thermal challenge in the 3D stack. So here, in terms of the performance, as a function of the TSV diameter, because TSV will take a lot of area. So here, if you look at the TSV, then the TSV diameter needs to be below like 1 micrometer to make the overall system competitive. So here, then this 1 micrometer TSV is still, challenge for today's industry offering. Industry's TSV today is roughly 10 micrometer square, 10 micrometer in that scale. So if you want to scale down to 1 micrometer, then still needs further improvements. And also we have to take care of the temperature. So here, with the lower diameter, the temperature goes up close to even 100 degrees C. So we have to take care of the temperature as well. And cryogenic, so we have to first benchmark the device transistor data at low temperature. And then we have to do the VTH engineering, because if you do nothing at low temperature, the device actually becomes worse. Even though you get better subsurface slope, but your on current also decrease. Then you have to move the VTH to here. So basically shift the VTH, and then you get the boost on current. Then you can improve the performance if you can re-engineer the VTH. And if you do that, then you can re-optimize the VDD, because now you re-engineer the VTH, and then you can lower down the VDD, and then you can improve the overall EDP at lower temperature and with lower VDD. And 3D NAND. So we'll discuss this more next time. So we can also use 3D NAND to do the computing memory, and we can support that. And but the 3D NAND has very limited peripheral circuits, so we have to use a separate logic die to do the peripheral circuits, and then do this bonding again with the 3D NAND. So with the 3D NAND, we can support large scale model, like gigabyte model, which is useful for today's, the large language model and other recommendation models, graph models. Okay, so let's talk about this technology update to 1 nanometer and these things support. So here, this is what we want to do. So the logic technology node is progressing towards this Angstrom era, 1 nanometer node. And there are many key features to be updated in the technology library. And so here we added those features into our technology library, like bin depopulation and standard cell height reduction, and DTCO and backside power delivery enabled the reduction of the standard cell size. And also the industry has transitioned from the FinFET to the gate-all-around stack on the sheet from the 3 nanometer or 2 nanometer node. And the future below 1 nanometer node will be the 3D CFET, complementary FET, like NMOS on top of PMOS or PMOS on top of NMOS. So here, then we have to continue to support those technologies in NeuroSim. And then with this kind of addition to the NeuroSim, we can support the new architecture, for example, the all-digital based computing memory DSIM, as proposed by TSMC in this SCC 2021 paper. So essentially, you have a SRAM with a local computation, like a NOR gate, like a 6 transistor SRAM plus 4 transistor NOR gate. You become 10 transistor cell into the local multiplication, and then in digital domain, and then with an adder tree, and then you can do the accumulation. So here in this design, you can still maintain the input parallelism. You can multiple many rows and then do the local computation, but then the accumulation is done by the digital adder tree. So then this will, be immune from the noise and the variations due to the digital computing, and is scalable to future 1 nanometer node. So we want to support this. So here, just to review some technological trend. So here we summarize the trend from the industry report and also based on the IRDS roadmap. So here, this is what we are going to use for the design in our libraries, and for 7 nanometer down to 1 nanometer node. In terms of the fin depopulation, eventually we only have 1 fin per standard cell, and then this is a standard cell height, contact pitch scaling, and fin pitch, and then the metal barrier thickness. So here, this is a general trend. This is, I think, IMAC report. So this is how we scale the standard cell height by fin depopulation and with the buried power rail. So then we can make the nanosheet based design. And then we have this FinFET to the stack nanosheet to the CFET eventually. So we capture those trend in our technology library assumption. And also we have to update some of the device parameters as well. So for example, the fin height, fin width, and then stack nanosheet thickness, nanosheet vertical pitch, and so on, and the EOT, equivalent offset thickness, and so on. So based on the projection. And then the reason is that we have to re-evaluate the on-state current and then proceed the capacitance of those newer generations. So that will determine, the on current will determine the latency, and capacitance will determine the CV square and the energy and so on. So the device parameters will affect the chip level, performance. So we have done some TCAT simulation to calibrate some of those parameters, because there's no industry, data at this moment. Even there is a 3-nanometer technology today, but there's no paper or public information, and so we have to do some projection based on our own understanding. So here, this is the eventual device input parameters from the TCAT simulation in terms of the on current, off current, and transconductance, and then bit capacitance, and junction capacitance. So those will be the parameters we use to evaluate the latency energy for those those new generations. And also the background line, the metal, needs to be carefully considered, because as we scale the technology node, then the interconnects will play more and more important role in terms of the delay, RC delay, and the power consumption. So here this is our assumption in terms of the pitch for the metal track, so for the lower metals and higher metals, and also we have to update the resistivity assumption, because the resistivity will quickly increase as we scale the pitch or the copper area due to the increase the surface scattering, grain boundary scattering, and also the barrier resistivity also will play a role when we scale down the technology node. So we have to update the resistivity as well. Okay, so for these things, then what is important is the critical path in the operation. So here, look, for example, here this is a initial benchmark, a 22-nanometer node, same as TSMC's report of that paper. So here then we have 256 by 64 array, and each cell is a SRAM plus NOR gate. So if you look at here is a SRAM and plus or NOR gate. So we can model those in NeuroSim. And then here, in terms of the delay, we have to consider the cell level delay and also the adder tree, especially the adder tree will become the critical path for the entire operation. So in the adder tree, we have to add the repeater if necessary to improve the latency. So here then this is all digital. So we can look at the critical path and then get the latency for the computation. So here this is the scaling trend, and this is this is for resident 18 Internet, and macro level means one subarray, and system means the entire chip. So here we have the technology node for futures 1-nanometer node, and you see that this sim could generally scale well with the scaling of the technology node for both TOPS per millimeter square and the energy efficiency. Here, I think this is TOPS per watt energy efficiency. So here, it's better than R1 for sure, and better than. So here, this SRAM is the analog SRAM. This DCM is what we discussed based on TSMC's design. So this SRAM is the analog SRAM. And so here, analog SRAM still is good in terms of the TOPS per millimeter square, because we don't have the adder tree. Adder tree is very, very expensive. But here, the challenge, for the SRAM is that still with the analog compute, you have the accuracy problem. And also here for the demonstration, TSMC reported the analog SRAM at 7-nanometer node. We don't know if the design will be also valid in future node or not. So here we believe that the DSIM is the only way to scale to future nodes. And then here in terms of TOPS per watt, it could reach at the system level hundreds of TOPS per watt, several hundreds TOPS per watt, which is for 8-bit by 8-bit computation. So if you look at some literature claim like more than 10,000 TOPS per watt, that is for 1 bit by 1 bit. So if you do that conversion, this will be like tens of thousands TOPS per watt if it's 1 bit by 1 bit. So it's very efficient if we do this DSIM using future technology nodes. So this is what we want to update for the future. And the final topic is that we also want to support the TPU kind of architecture. So the TPU architecture is based on digital MAC operation. And then there's a simulator called Time Loop, developed by MIT and NVIDIA. So it is a simulator to look at the traces of the digital systolic array, like TPU. So what we can do is to take the traces from the time loop and then coupled with our NeuroSim hardware estimation, because essentially the time loop give you the number of access, for example, the number of MAC operations, the number of memory access. Then we just multiply by the number of that with our NeuroSim hardware estimation, like area latency for each access or for each MAC operation. So then we can get the final TPU performance. And even in the future, we want to also build an interface with the Gen 5 for CPU and GPU workloads, and eventually for the chiplet-based system. So anyway, so here let's look at one example. So this is a TPU architecture. We have many digital MAC, and here there's a global buffer, it's on-chip cache. So we want to look at what kind of emerging number-type memory could replace SRAM for this global buffer. So here we have all those candidates. Besides the FE and MRAM, we have one more, which is 2T gain cell. This is embedded DRAM, EDRAM. So it's based on 2 transistors, and then this node will temporarily hold the charge. Then this could be used as the DRAM. So those 2 transistors could be the backend offset transistor. So this is fully 3D modelistically integratable. So here, then this is the settings for the benchmark. We have considered 2 scenarios, the cloud and edge. Cloud is 3 nanometer, edge is 22 nanometer. Clouds run higher frequency, edge run lower frequency, and then the different sizes of PE. And then for the edge, we have 22 nanometer design options. For cloud, we have 3D version. So basically, as we just discussed before, so back-end of LAN memory at lower technology node, older technology node. And front end of the line, we still use most advanced, in this case, 3 nanometer node. So this is a 3D projection. So then this is the flow, as we mentioned earlier. Based on the time loop, we get the number of accesses, and then from our NeuroSim, we get the hardware estimation. So here, this is the result. For cloud TPU, still the SRAM, this is normalized energy and normalized the chip area, normalized to the SRAM baseline. So many of the number-type memory still has worse energy than the SRAM, even though they can lower down the area a little bit. So similar situation for the edge. So the only better energy technology is this EDRAM based on this 2T gain cell backend of line. This could be a little lower than the SRAM in terms of the energy. And also it could reduce the chip area significantly. So we believe that this 2T gain cell is a good candidate for the on-chip buffer. Because the buffer, you don't need to store the data for a long time. You need to update the data anyway. So the EDRAM is good. It can store the data for maybe a few seconds, and then that's good enough for most of the applications. So we believe this is a good candidate, the backend of line 2T gain cell for the global buffer for the TPU kind of accelerator. Okay, finally, then we want to extend our NeuroSim platform to this 2.5D and 3D heterogeneous integration system with the support of the TSV and the hybrid bonding and so on. So we will discuss it more in the next lecture when we talk about the 3D IC design. So this is ongoing effort. All right, so for the rest of the time, I will quickly show how to run this NeuroSim very quickly. If you want to do it by yourself, you still need more exercise. So basically, after you go to the GitHub and clone that to your own account, and then you can run it. The C++ CPP files consider 4 categories for input: the parameter files, a circuit module, and then the subarray and the main CPP. So here you can modify some of those files according to your needs. So let's look at some of the files you want to modify. For example, if you have different technology, different device parameter, then in the run.cpp, then you can choose different option like SRAM, RRAM, or FEFET. Basically, RRAM, not just RRAM, basically two-terminal resistor. It's the cell type 2. And then you can define the cell precision. That means each memory cell can store 1 bit, 2 bit, or 3 bits. So then you can define the cell size for the SRAM and also the non-volatile memory in terms of the on-state, off-state resistance, on-off ratio, and read-write pulse condition. So those are the parameters you can change based on your own technology. And then for the update, so we have this new standard cell height and also the SRAM sizing at the newer technology node. So this is down to the 1 nanometer node. And then for the circuit level, you can choose the technology node, and then you can define the subarray size like 128 by 128. And then you can choose different ADC and ADC precision. So here we have the ADC like the current mode, voltage mode, and SAR ADC, and the flash ADC, and so on. And also the sharing, right? So 8 colon share 1 ADC, for example. You can choose those numbers. You can change those numbers. And also for the wire width, we have updated the wire assumptions in the new Wave 1.4 version. So this will be the new resistivity depending on the width of the wire. And then here for the transistor model, then we have updated. So for the old technology node, we use the PTM model. And then for the new technology nodes, then we have to manipulate the numbers, and from our TCAD simulations, we change the numbers like the cap and on current density and so on, and here. So then those are the low level, like device level, circuit level parameters you can change. And then this will be the high level parameters, like the, for example, here, the precision of the neural network model is all 8 bits. For the weight, gradient, arrow activation is all 8 bits compensation. And also the hardware, you can do it in parallel modes or a pipeline or a sequential mode. And then you can, if you turn on those non-ideal effects like variation, retention, then you can get the accuracy under those assumptions. So here, then the circuit modules are all stored under this folder, folder. And then, for example, the adder tree has its own model. So we use a very simple 3-bit replay carry adder, and then this is extendable to n bits. So we can estimate the adder tree using the modules as we defined in this file. So within the adder tree, then we have the precision and clock frequency, and then the MOS, PMOS width, and so on. So the sizing, we have a little bit of sizing, but then, as I said, we cannot flexibly adjust the sizing. So the sizing is one time and predetermined of the transistor size. So here we have to consider the area for those standard cell, and then for the gate-all-around stack nanosheet, we have some special design rule for that. So here is a special design rule in more details. And also we have to fold the transistor size a little bit if you want to optimize this a little bit. And also for the latency, then eventually we are based on this Horvitz equation, and then basically RC delay for the latency. But mostly the latency is based on this Horvitz delay equation, based on the input ramp rate and the load. And then circuit RC modeling is basically RC, and then this gate delay, wire delay, and then this propagation delay through this Horvitz equation. And for the power, as I said, the dynamic power CV square for all loads, we have to consider all the contributions from the capacitance, from the parasitic capacitance as well. And then the leakage is off. We have to consider which circuit module is in the idle, and then we have the leakage power for all gates that are in idle. So here then we can support different neural network model, but by default we support like ResNet, VGG, and so on. But if you want to define your own model, you have to retrain your network. So here you have to make layers function. This is at the PyTorch. Then you have to change the kernel size, number of kernels, and stride, and so on. So you have to define your neural network model here at the very top level. For example, here, if you create your own model, you have to provide like a table like this. Then you can. This is an example for VGG8, but if you want to change your model, you can change the parameters. Then you have to retrain the model and then get the accuracy. But if you do not want to retrain the model, then we provide some default model to use, and VGG is one of that as a default model. So this is the overall flow. So you change all the parameters you want to change, the device level, circuit level, then you compile, and then here, if you use our default model, you can bypass this one. You can generate the output right away. But if you want to create your own neural network model, you have to create the model file as showed in the previous slide. You have the table, and then you retrain it and create this traces, and then run the inference of the hardware. So this is the workflow. And finally, I show some output example. So here, for example, you can get the accuracy like 90%, and then you get the mapping. And so how many tiles are used for each layer? For example, layer 1 use 1 tile, layer 2 is 1 tile. And speed up means the duplication. With duplication, layer 1, as we discussed earlier. So we duplicate the width 16 times to speed up. So then this is the information you will get, and then performance breakdown. And overall, let's say for each layer's breakdown, like layer 1, latency, energy, then power, leakage. So and for different components, like the ADC accumulation and other peripheral circuits, so you get the detailed breakdown of the latency and the power. And then this is the final summary for the entire chip level, the total chip area, and then total latency, and then total energy. And eventually it will calculate the TOPS per watt, like 24 TOPS per watt, and then TOPS and the TOPS per minute square. And finally, the simulation time, and 151 seconds running this example. So this is how it look like if you run the NeuroSim. So here are some references if you want to look some details of the tool. But we provide a manual, instruction and manual, so you can also refer to that. All right, so I think that's pretty much what we want to share today. And we still have a few minutes to take some questions. So any questions?你这儿有什么问题吗？
有老师或同学有问题的可以提问哦。
今天好像没有什么问题。
好，那如果老师或同学没有问题的话，那于老师，那我们今天的讲座是否就提前结束呢？
可以，没问题。
好，那谢谢于老师，还有各位老师及同学的参与。OK，谢谢。
OK，拜拜。
OK，拜拜。